Dear participants, welcome to 9th International Symposium on Multidisciplinary Studies and Innovative Technologies. So, the conference is supported by IEEE Turkey section and also supported by Tokat Osman Paşa University. So, we are in session 5.2 now, and we have 12 papers to be presented in this session. Each participant will have 10 minutes to present their studies. So the title of the first paper is Constructing a Novel Dataset for Android Bug Prediction. Are the authors here? I think the author is here, but can you hear me? Emily says.
Yes, I can hear you.
Okay, you can share your screen.
Okay, I will start to present my paper.
Okay.
Okay, I will try to share my screen. Just a minute, please. Okay. Just a minute. Okay.
Okay, you can start.
Yeah. Good morning, all. To begin, I would like to express my sincere gratitude to the organizers for providing us with the valuable opportunity to present our research, exchange knowledge, and learn from other studies. Let me briefly introduce myself. My name is Amani Sayes. I hold master's degree in software engineering from Beirut University, and I have over 10 years of a professional experience in software engineering field. The study I'm presenting today is part of my master's thesis. In today's presentation, okay. On today's presentation, I will start with a quick introduction to our study covering the research problem, aim, and objective. Then I will briefly go through the related literature, research methodology, and the evaluation technique we used. After that, I will present the main result and discussion. Finally, I will conclude with the key findings of our work. Okay, today, mobile apps are part of everyday life, but debugging them is still difficult and time-consuming. From my 10 years of experience in software engineering, and according to studies, developers spend almost half of their time fixing bugs. To reduce this effort, researchers use machine learning to predict bugs and early highlight the most error-prone parts of the code. But Android apps are more complex than traditional software apps, and their bugs are different. So traditional bug prediction models don't work well for Android apps. This is why we need models designed specifically for Android application. So, the main aim of this study is to create a suitable bug dataset that can be used to build Android production model. In addition, the study focused on handling the class imbalance problem in the constructed dataset, since this issue can strongly affect the performance of production models. Finally, the study aims to identify machine learning algorithms that can provide better performance and accuracy for predicting bugs in Android application by using the constructed dataset. So, in this study, we are trying to answer three main questions. First, how can we build a good Android bug dataset using source code metrics. Second, how can we handle the class imbalance in that data set? And third, which algorithm like random forest, support vector machine, logistic regression, naive Bayes, or neural network give the best result for predicting Android bug with this dataset? Okay, two, okay. Uh, تمام. To achieve this objective, we to achieve this objective and answer the question, we first review the existing literature, then we set up our research methodology and create the proposed dataset. After that, we build the bug prediction model using this dataset as input, and finally, we evaluate the model to see how well it works. تمام. In literature review phase, we look at the previous study and organize them into 4 groups. First, source code metrics, which focus on how metrics are used and evaluated for bug prediction. Second, machine learning algorithm, which looks at how machine learning is applied and improved in this area. Third, the combination of metrics and machine learning, which shows how using both together can give better prediction. And fourth, bug dataset, which covers things like class imbalance and introduction of a new dataset. After that, we clearly present the study objective. The first objective is to build a new bug data set and test its suitability. The second is to identify the best performing machine learning algorithm. The third is to evaluate how imbalance handling methods such as smart and undersampling affect the result. Then we move to the next phase, which is creating bug dataset. We decide to use open source project because they give us give many options and greater flexibility when selecting a project. After that, we choose GitHub to our project source since it's widely used and provide helpful features such as labeled bug report and issue to commit linking that make it easier to identify bugs. In the selection project phase, we define the criteria to help us to choose right projects, such as the programming language and number of closed bugs. Based on these criteria, we selected 4 projects to build our proposed dataset. The selected project, and these figures show a comparison between the selected project. Next, the next step was measuring the source code metrics for this project. We tested several tools, and finally we choose source meter tool because it can measure a wide range of source code metrics. However, in our study, we focused only in class metrics. The process of creating the dataset include many details steps, but because the time limit, I will give short summary. In our paper, we discuss and explain these steps. First, we evaluate each project release to decide whether to include it or discard it. Next, we use a GitHub bug tracking system to identify which parts of the code caused each bug. After that, we used Panda library to filter, normalize, and merge the data from several Excel files. In the end, our final dataset includes 7,530 instances, 6,844 negative instances with bug count of 0, and 690 positive instances with a bug count of 1. Okay. As we can see, our dataset is imbalanced, which is expected given the type of a problem we're trying to address. To handle this, we applied several techniques to balance the dataset, include random undersampling and smooth. Okay, in the evaluation part, we tested the dataset with these methods using 5 different machine learning algorithms: random forest, support vector machine, logistic regression, naive bayes, and neural network. Each algorithm was tested under 3 conditions: without pre-processing, with smooth, and with random undersampling using the same dataset. We apply tenfold cross-validation to ensure reliable result.
Sorry, your time is finished. Please try to summarize and conclude.
Yeah. Okay. تمام. The final result of a conducted experiment demonstrate good performance with F1 score okay. With F1 score above 94% using smooth resampling, and above 71 with the random undersampling. Overall, the random forest algorithm outperformed the other algorithms. Okay. Overall, this approach demonstrates the systematic way to build effective bug prediction model for Android application, providing insights that could help improve software quality and reduce debugging effort. Thank you.
Okay, thank you for your presentation. Are there any questions? Okay, let's go on with the next paper. But before the next paper, dear participants, once again, I would like to remind you that because of the fact that we have many papers in this session, each participant will have 10 minutes to present their studies. So the title of the next paper is Interpretable Classification of Laminar and Turbulent Flow Using Gated Deep Learning Models with SHAP-based Explainability.
Can you hear my voice?
Yes, we can hear you.
Thank you. Let me share my slides.
Okay.
Can you see my slides?
Yes, you can start.
Thank you. Hello, everyone. My name is Burçak Asal. I'm an assistant professor from the Adana Alparslan Türkiye Science and Technology University from the Computer Engineering Department. Today, I will present you my study interpretable classification of laminar and turbulent flow using gated deep learning models with SHAP-based explainability. Firstly, as an outline, I would like to introduce and make problem definition of my study, and then I will introduce my dataset, utilize dataset and methodology, especially utilize models with gate and Gandalf models, and the integrated explainable AI technique, which is Shapley additive explanations method. Lastly, I will introduce my experimental details and results, and I will conclude and mention the future work of my study. As an introduction, turbulence and fluid flow, we can say that is nonlinear and especially hard to model analytically. With respect to that, CFD data, aka computational fluid dynamics data, offers rich features but require artificial AI or different machine learning techniques for especially proper pattern recognition. Uh, with that concept, gated deep learning models handle tabular interactions effectively, especially with I will introduce gate and Gandalf models. Another aspect is that interpretability also helps trust artificial intelligence on ML-based decisions. Uh, my study's problem definition is that as a task, we can say that it is binary classification of flow type. Class 0 represent laminar flow and class B represent turbulent flow. Especially, task needs the prediction from different features such as velocity, pressure, and other gradient features. As an output, we can say that data's output is a two-based binary flow type label, which I mentioned before. As dataset description, uh, my dataset used is a computational fluid dynamics dataset from the Kaggle. It includes approximately 10,000 samples with the 12 input features, as you can see here. It includes many different aspects of the flow, such as time coordinate, x and y coordinates in the channel, x and y velocity components, pressure component, spatial derivative of u with respect to x and y, and spatial derivative of the v with x and y, and lastly, spatial derivatives of the u and v with the temporal derivatives. As another description, I also extract the correlation matrix, which represent the pairwise correlations between the features. Uh, as you can see here, most obvious relations it P and X, which is a highly negative correlation, and Y and du dy, which is also as a negative correlation. Also, V and dv dt and U and du dt has a obvious more positive correlation with respect to the other combinations.
وعليكم السلام. هلا سنة أبجد نجمي جميع
Uh, as I utilize models, as I utilize models, I my first model is the gate model, which aka which is the gated additive tree ensemble. This model combines the decision tree additivity as DNDT, differentiable nonlinear decision trees with a neural gating mechanism inspired from the gated recurrent unit models and self-attention mechanism. This model basically learns the three components and which three components activate per input with the self-attention. It's also able to capture local and global feature effects. My second model is the Gandalf model, which is the gated adaptive network for deep automated learning of features. It also includes hierarchical GFLU, which is the gated feature learning unit modules that route information dynamically. These methods also ability to learn complex tabular interactions end to end and design for robustness and scalability. Uh, my experimental technique integrated these models is SHAP, which is Shapley additive explanations. It basically values to quantify feature impact and feature importance between the features, and it especially measures global importance ranking and local decision explanations. But we can choose to use that as a global interpretation, not local with the SHAP. SHAP explainability technique applied to the best model, which is Gandalf, which I will show you in my later slides. My experimental results is here. As a train validation test split, I use 80, 10, and 10% respectively. I also shuffle the dataset to ensure distribution balance between the batch with respect to the learning process of the models, and finally, our target feature, which is the ground truth feature, encoded as a binary label with 0 or 1. Here are my models, gate and control models, performance comparison table. As you can see that both models generally give high performance results, especially to different measurements, which are the precision, recall, F1 score, and accuracy. But we can also see that Gandalf models slightly outperforms gate models with the general metrics, especially with an accuracy. And here are again my experimental result, visual result with respect to the different shape perspective based plots, which is the first one is the shape bar plot, which represents the feature importances between the blue bars. We can see that especially P, dV, dy, and V and dV, dt features are more important features between the decision of the Gandalf model with respect to the other features. Our second plot is the shape summary plot, which is again gives same information between the features but different perspective, which is the plot of the features, plot of the test points within the test set. As you can see here, again, P, dV, dy, V, and dV, dt features are more important in the model decision process compared to the other features. Especially high plots, high colored plots with the red plots represents the feature values, and these are the shape values between the negatively or positively affects the model, whether depend on the situation. Our last plot is the shape decision plot, which again shows the same condition P, dV, dy, V, and dV, dt features with the cumulative decision lines within the model's decision process. As you can see here, in the especially P features, the separation is more clearly observable within this P feature or dV, dy feature. As a discussion, we can say that both gate and Gandalf models achieve near perfect classification, but Gandalf model offers slightly higher performance compared to the gate model, and other conclusion can be observable that pressure and velocity gradients especially influence transition model decision by obtained our shape explainability analysis. As conclusion and feature work, gated models effectively, we can see that classify laminar vessel turbulent flow classification, and SHAP technique further validates the feature importance aligned with physics. Proposed approach bridges the CFD and explainable AI. For future work, I also explore the local explainability techniques such as LIME and other techniques, and analysis and ensemble-based methods such as stacking are also planned for integration. These are my references. Thank you for listening. If you have any question, I can answer it. Thank you.
Okay, thank you for your presentation. Dear participants, do you have any questions? Okay, let's go on with the next paper. The title of the paper is Enhancing LVRT Capability in Grid-Connected PV Systems Using DRL-Based Controller During Ambulance Faults. You can share your screen.
Okay. Hi everyone, I am Büşra Özgenç. I am a research assistant at Karadeniz Technical University. I will present enhancing LVRT capability in grid-connected PV system using deep reinforcement learning-based controller during unbalanced faults. As outlined, I will mention introduction, design of control methods for LVRT capability, simulation results, and conclusions. Falling costs of renewable energy have increased their integration with microgrids, but their intermittent nature pose challenges for maintaining grid stability. Despite this, renewable sources offer benefits such as fault right through. Initially, grid codes required renewable sources to disconnect during faults, but their widespread adoption led to grid instability and energy shortage. To address these, countries like Germany, Italy, and Japan update grid codes to require low voltage right-through capability, ensuring renewable systems remain connected during faults. The LVRT capability aims to maintain system stability by providing reactive power support. As PV systems have become common, LVRT control has become a critical requirement. The German grid code mandates that PV systems stay connected for 150 milliseconds during voltage drops to 0 per unit. Voltage must recover to 0.9 per unit within 1.5 seconds to comply with grid code requirements. In addition to LVRT capability requires the management of AC overcurrent and DC overvoltage. And also reactive current step response must meet performance criteria, including a rise time less than 30 milliseconds and settling time 60 milliseconds. And the current value must remain within a tolerance range as shown. The inverter-based control methods, deep reinforcement learning techniques have demonstrated notable success in energy applications such as reactive power management and voltage control and in IEEE bus systems. These advancements underscore the growing potential of deep reinforcement learning to transform energy system operations. This paper aims to achieve LVRT capability in a two-stage, three-phase grid-connected PV system. The PV system is modeled in MATLAB Simulink and controlled using SAC and TD3 algorithms and tested under single-phase fault and double-phase fault. To evaluate its effectiveness, the performance of these algorithms are benchmarked against PI controller optimized by SOS algorithm. The system is developed using MATLAB Simulink with its parameters specified in the table. This paper uses reactive current injection and DC chopper circuit for the LVRT capability. DC chopper includes a switch and series resistor. During a fault, DC chopper circuit activates to prevent active power imbalance, ensuring both DC bus voltage limit and operation at MPP of the PV array. Additionally, DC bus voltage is kept 1.1 per unit to prevent device damage and avoid grid disconnection. According to Germany grid code, reactive current depends on voltage level as in 2. Since inverter current is limited, active current must be reduced during faults as in 3. The maximum inverter current is in this paper is set to 1.2 per unit. Reference values for grid side active and reactive powers are calculated as in 4. As depicted in figure, duty cycle and reactive current values are adjusted by a PI controller to track reference power values. SOS algorithm is employed to optimize PI controller parameters. The simulation is conducted for a duration 2 seconds with 0.33 per unit single phase fault lasting 150 milliseconds applied at 0.5 seconds. The objective function is defined as int5 and with concentrates for grid current and DC bus voltage. Optimization parameters are provided in the table. In the deep reinforcement learning based LVRT control,
Okay, let's go on with the other paper. I think the connection lost. Just a second. So the title of the next paper is a prompt engineering methodology for evaluating large language models in academic processes.
Yes. Thank you very
You can
much.
share your screen.
Yes.
But please, can you just hold a second?
Yes.
The connection of the previous participant stopped, and I think she's now entering again. Just please wait. Okay, you can start.
I suppose you can see my screen.
Yes.
Okay, thank you very much. I'm Ioannis Pathias. I'm from the university, from Sofia University, the Faculty of Mathematics and Informatics. And together with my colleagues, Michaela Georgieva and Plamen Totev, we prepared this work, which is a prompt engineering methodology for evaluating large language models in academic processes and not only. So the main idea is that with the rapid evolution of artificial intelligence and NLP methodologies, prompt engineering has become an essential technique for optimizing the performance of large language models. So we proceeded by defining a systematic approach, which is based on selection of use cases, choosing the right LLM per case, selection of prompts appropriate for the LLM in the case, and choosing the appropriate validation metrics for each of the above. So despite the significant progress in the field of prompt engineering, there remain several challenges and open questions. Such challenges are the lack of standardized evaluation metrics for prompt engineering and the need of a comprehensive benchmark to assess the efficacy of different prompt engineering techniques. So the methodology is to evaluate the performance of LLMs through prompt engineering as a detailed methodology, which is crucial. The methodology selection outlines the experimental setup, including the selection of LLMs and data sets, the design of task-specific prompts, and the evaluation metrics used to assess effectiveness. The methodology ensures a comprehensive understanding of how prompt engineering techniques can optimize LLM capabilities, offering insight into practical application and potential improvements. The experimental setup we used consists of prompt defining, LLM defining, LLMs answers collection, the evaluations of the LLMs according to accuracy, user satisfaction, precision, and execution time. And then we have respectively the evaluation of the results. The designing of the prompts was a key aspect of the study, tailored to each task's objective. For text classification, prompts were crafted to elicit accurate labels, while for question answering tasks, they aimed to extract precise answers. Prompts were created through both manual crafting using expert input and automated generation, which produced a variety of prompt variations. An iterative process was employed to refine the prompts. Initial designs were tested, evaluated, and adjusted based on the performance, ensuring continuous improvement and optimization. So, in terms of evaluation metrics to assess the performance of the prompt engineering techniques, a set of evaluation metrics was employed. These metrics were selected to provide a comprehensive view of the model's performance across different tasks and prompt designs. Accuracy for tasks such as text classification and question answering accuracy was used as a primary metric. It measured the proportion of correctly predicted labels of answers, providing straightforward state assessment for the model's efficiency. User satisfaction to complement quantitative metrics, qualitative user feedback was collected. Participants interacted with the model using different prompts and provided their assessments of the quality and relevance of the model's responses. The feedback offered value insights into the practical effectiveness of the prompts. Precision. These metrics were particularly relevant to classification tasks, as precision measured the proportion of the true positive prediction out of positive predictions, while recall measured as a proportion of true positives out of the actual positives. Execution time, response time was recorded to assess the computational efficiency of the prompts, ensuring high-quality prompts did not significantly slow the model. It's important to note that the response time can also be influenced by the model's load at a given moment. The results. This section presents the empirical findings from our study on prompt engineering by evaluating the performance of GDP3 and GDP4 across different domains. We aim to highlight the effectiveness of various prompt designs. The section provides detailed examples for the fields of academic processes, finance, healthcare, and engineering. And the domain with a responsive task. For academic processes, we had the task of student assessment and preparation of materials. For finance, we had tailored finance advice and explain complex concepts. For healthcare, we have patient-friendly health information and medical professionals reports. And for engineering, we have project management plans and complex engineering problems as cases. The conclusion is that the study highlights the critical role of process engineering in enhancing the performance of LLMs across academic and other domains. Our methodology demonstrates that well-designed prompts significantly improve outputs in accuracy and relevance in education, finance, health, and engineering. In conclusion, this study provides a robust framework for prompt engineering, offering valuable insights and practical guidelines for researchers and practitioners in academic domain. The proposed methodology not only bridges the gap of standard-type prompt design, but also paves the way for future research to explore innovative prompt engineering techniques tailored to academic contexts. As future directions for our research, we see advanced prompt engineering strategies, adapting the LLM to different languages and specific fields, and better mechanism for evaluation and detection of inaccuracy. Thank you very much for your attention. If you have any questions, please.
Okay, thank you for your presentation. Are there any questions? Okay, thank you.
Thank you
So
very
the
much.
connection of the previous participant stopped, and now she will go on presenting.
I'm sorry, this problem. I continue. In the deep reinforcement learning-based LVRT control, the agent receive 12 one-dimensional observation values, and the agent, these observations are mapped to two-dimensional action space, and the reward function is designed to ensure the reference power values are tracked according to voltage level during faults, and to keep DC bus voltage and AC grid current with defined limits. And the defined reward function is given here. Using training parameters and agent parameters, TD3 and SAC algorithms were trained, and for TD3 algorithms, the training lasts approximately 114 hours, and SAC algorithm, the training lasts approximately 46 hours. During the test phase, to analyze dynamic response, fault was applied in 0.5, 0.65 second range in a simulation that run for a total 2 seconds. In the results, for single phase faults in SAC algorithm, low error values were obtained in 2 out of 6 values according to SOSPI controllers, and 3 out of 6 values according to TD3 algorithms. For two-phase faults, SAC obtained low error values in all faults according to SOSPI, and according to TD3, SAC obtained lower error values 4 out of 6 values. In the here, response to 0.3 per unit single phase faults are provided. In general, increasing amount of system oscillation has complicated the decision-making structure of the controllers and reduced their generalization capability. These tables provide dynamic response obtained for each controllers during single-phase and double-phase faults. In terms of generalization dynamic response for fault values, SAC algorithm showed most generalization capability. As conclusions, this paper explores how deep reinforcement learning methods can improve LVRT capability of grid-connected PV systems under unbalanced faults. Simulation results indicate the deep reinforcement learning algorithms give higher error rate compared to conventional method. However, when looking at the dynamic response, SOS-PI controller can only generalize one fault, while TD3 agent 3 faults, and finally SAC agent can generalize 8 faults. This suggests that SAC algorithm provides a more generalizable and robust solution under different error conditions, highlighting its potential as an effective control method for LVRT applications. Thank you for listening.
Okay, thank you. Are there any questions? Okay, let's go on with the next paper. The title of the paper is Comparative Study of Classical ML and Deep Learning on Small EEG Datasets.
Good morning, everyone. Today, I'll be presenting our comparative study on classical machine learning versus deep learning on small EEG datasets. This work was conducted by Dr. Ali Berkol and myself, İdil Gökçe Demirtaş. Our study explores how classical machine learning and lightweight deep learning methods compare when applied to small EEG datasets, a very common challenge in neuroscience and affective computing research. The main objective of our work is to systematically evaluate how classical feature-based ML models compare with lightweight deep learning architectures when working with the limited EEG data. We designed subject-independent experiments, meaning that tests of subjects were never seen during training to ensure fair generalization. We also compared not just accuracy, but robustness, model size, and computational cost. This way, we could draw realistic conclusions for real-world EEG applications, such as emotion recognition and cognitive state detection. EEG data is incredibly rich, but it's also noisy, subject-dependent, and hard to collect in large quantities. While deep learning dominates in other domains, its success relies heavily on large-scale datasets. In small EEG studies, that assumption breaks down. We therefore designed a systematic comparison where both ML and DL are tested under the same experimental conditions to ensure fairness. We base our experiments on two well-known EEG datasets. First of all, the DREAMER datasets includes 23 participants and 18 emotional video sessions recorded with 14 EEG channels at 128 Hz. Second, the Amigos dataset contains 40 participants, but we use that reduced subset of 10 subjects and short video trials to simulate a low data scenario. Both datasets focus on emotion recognition, which makes them ideal for testing generalization under limited data conditions. Our pre-processing pipeline included bandpass filtering, actually between 1 and 45 Hertz, notch filtering at 50 Hertz, and segmentation into 2-second windows. Then the data splits into two parallel paths. The first branch extracts, features, and trains classical models such as SVM, random forest, and logistic regression, while the second feeds raw EEG signals into lightweight CNN based models, EEG-net, and a compact one-dimensional CNN. This allows a one-to-one comparison between feature-engineered and end-to-end approach. For clarity, actually we express our workflow in two pseudocode blocks. Algorithm 1 describes the feature extraction process, computing spectral, temporal, and statistical descriptors for each channel, such as power spectral density, differential entropy, and Yort parameters, and also higher order statistics. Algorithm 2 summarizes how tiny EEG-net is trained using small batches, dropout regularization, and early stopping to prevent overfitting. This structure ensures full reproducibility, and we also open source our implementation for future benchmarking. To guarantee fair and unbiased comparison, we use two subject-independent protocols. First, leave one subject out, where each participant is held out once for testing. Second of all, a subject disjoint 80-20 split, where training and test subjects never overlap. We measured accuracy, macro F1 and ROCA-UC, and tested significance using the Wilcoxon signed rank test. We also compared model size, number of parameters, and inference latency, which is essential for real-world and embedded EEG applications. The results were clear and consistent across both datasets. Classical ML models, especially SVMs, perform slightly better or on par with lightweight deep learning architectures. EEG-net and 1D, one-dimensional CNN came close when minimal data augmentation and proper regularization were used. Statistical tests showed no significant difference between SVM and EEG-net, meaning both approaches perform comparably in small data regimes. However, deep models offered faster inference once trained, whereas ML methods were simpler to train and tune. These results highlight that the best choice depends on the data scenario, actually. In low data situations, which are very common in EEG research, classical ML with handcrafted features remains reliable, interpretable, and computationally efficient. As datasets grow and augmentation or transfer learning is applied, lightweight DL models begin to outperform traditional ones. So rather than seeing ML and DL as competitors, we view them as complementary approaches, each valuable under different conditions. To conclude, our study provides evidence that classical feature-based ML remains highly relevant for small EEG datasets. Deep learning can match this performance only when augmented and regularized carefully. In future work, we plan to extend this comparison to more data sets and integrate data-efficient learning methods such as self-supervised and hybrid models. So thank you very much for your attention. I'll be happy to take any question.
Okay, thank you. Dear participants, do you have any questions? Okay, let's go on with the next paper. The title of the paper is Prisma Guided Systematic Review of Large Language Model LLM Applications in Business Intelligence.
Hello, everyone.
Hello.
Is it okay now?
Yes, you can start.
Okay. On this slide, I will briefly introduce what we mean by business intelligence and why large language models are relevant in this context, and what kind of challenges exist in traditional BI environments. Business intelligence, or BI, can be understood as a set of architectures, tools, and methods that help organizations turn raw data into something meaningful and useful. Instead of just storing data in databases, BI focuses on creating insights that people can actually act on. In practice, this includes things like standard reports, interactive dashboard, any analytical workflows. All of these are designed to support data-driven decision-making across different levels of the organization and from operational teams to top management. Large language models are interesting in this context because they can sit on top of existing BI systems and provide a natural language interface. Instead of writing SQL or learning complex BI tool, users can simply ask questions in everyday language and receive explanation in conversation way. More concretely, LLMs can translate natural language questions into text to SQL, help interpret database schemas, and guide users through conversational analytics. This lowers the technical barriers and makes advanced analysis accessible non-technical stakeholders. When we combine LLMs with retrieval augmented generation, they can also use up to date enterprise document and data as context. This means that the model is not only relying on what it has learned during pre-training, but is actively grounded in the organization of data sources. Typical challenges in traditional BI. However, traditional BI still faces several challenges. Many business users cannot directly work with data. They depend on technical experts or data teams to write complex queries or build new reports. This dependency slows down the analytical process. The tool themselves often have a steep learning curve. Users need to understand SQL, data models, and specifics of each BI platform, which is not always realistic in busy business environments. As a result, there are slow iteration cycles between asking business questions and actually receiving reliable analytical answers. Questions need to be translated into technical requirements, implemented, validated, and then interpreted again for business stakeholders. Growing number of studies. There is a rapidly growing body of the work on LLMs in BI, especially around natural language querying and the text to SQL. However, these contributions are fragmented and often limited to small domain-specific case studies. We still do not have a semantic framework that explains how LLMs are integrated into BI workflows in a consistent way. Therefore, a Prisma-guided systematic review is needed to consolidate the evidence, map the landscape, and identify open source questions. Our study is designed to fill exactly this gap. Our overall objective is systematically examine how LLMs are integrated into BI workflows. More especially, we look at how these systems are embedding in the BI, and in BI, we compare the methods, LLM types, BI layers, and evaluation approach across the selected studies. This study is designed as a systematic review and follows the PRISMA 2020 guidelines. We explicitly reported the case steps such as eligibility criteria, search strategy, study selection, and synthesis. We searched 5 major electronic database and digital libraries: Web of Science, ACM, Digital Library, Springer, Link, IEEE Explorer, and Google Scholar. All research were carried out up to May 2025 to capture the most recent work. Our core search terms were business intelligence and business intelligence artificial intelligence. These terms were applied to title, abstract, and keyword fields, and we restricted the publication years to period from 2020 to 2025. Title, abstract, and full text screening were conducted independently by 2 reviewers. In total, we started with 265 records, and after applying the eligibility criteria, we arrived at 15 unique LLM BI studies that were included in the final synthesis. We organized all included studies in a common Excel-based coding matrix where each row corresponds to a single article. For each study, we required basic bibliographic information, citation count, publication year, title, and authors. We also include article summary column, which stores the abstract or consistent summary of the paper so that we can quickly recall its main focus during analysis. We then coded technology usage through a simple binary flags indicating whether each user's study uses RAG or an LLM and classical NLP techniques or image processing components. For studies that involve LLMs, we added dedicated fields for the LLM type, details on how it's used, and application domain, and the way it's integrated into the BI workflow. This helps us compare not only whether an LLM is present, but also how it actually operates within the system. First, LLMs act as a natural language interface to BI. They interpret user questions, map them as table schemas, and generate the correct SQL queries. Second, RAG-based assistants combine LLMs with enterprise reports and dashboards. This allows them to give explanation summaries. They are grounded in real organizational data. The review relies on what the original studies report as performance metrics, usage context, and studied benefits or limitation. Many contributions remain at the level of architectural proposals or prototypes with heterogeneous metrics and data sets, which makes standardized comparison meta-analysis impossible. And to conclude, this paper provides a PRISMA 2020 guided systematic overview of how LLMs are generally used in business intelligence. Our review shows that most existing work focuses on the user interaction layer and remains largely exploratory. Based on these findings, we propose a research agenda and conceptual framework to guide more integrated and robust BI LLM systems. Thank you for attention. Any questions I can get?
Okay, thank you. Are there any questions? Okay, let's go on with the next paper. The title of the paper is Multi-Agent Adversarial Training for Text-to-Image GANs. Our daughters here. Okay, they are not here. Let's go on with the next paper. A sensor-based system for cardiac activity tracking with integrated remote monitoring capabilities. You can share your screen.
Okay, do you hear me?
Yes, you can start.
My name is Krasimir Cheshmedjiev. I am from Institute of Robotics at Bulgarian Academy of Sciences. The topic of today's presentation is a sensor-based system for cardiac activity tracking with integrated remote monitoring capabilities. The presentation will The presentation will take place in the following order: small introduction, materials and methods, results, conclusions. The cardiovascular system ensures oxygen and nutrient delivery through the body and its proper functioning as vital for human health. In the post-pandemic era, remote monitoring of patients has become increasingly important to guarantee disease control and equal access to healthcare, even in small or remote cities and villages. Internet of Things technologies enable continuous monitoring of cardiac activity in patients at risk, offering permanent interconnection of body sensors, cardiology software, and biomedical databases. The system proposed in this paper is built by combining multi-sensor PPG registration, ACG air Holter monitoring, ensuring redundancy, reliability, and comparative signal analysis. This slide illustrates an IoT-based architecture for continuous cardiac monitoring. The proposed system demonstrates how IoT frameworks allow continuous HRV monitoring by integrating body sensor networks, wireless gateways, and cloud-based analysis, thereby enabling clinicians to detect heart rate risk patterns outside hospital settings. IoT applications integrate cloud technologies, GPS, smartphones, and machine learning, while wearable sensors like ECG, PPG, blood pressure, oxygen saturation, and motion enable continuous monitoring and crisis alerts. This slide shows the registered PPG signals after analog to digital conversion on the picture on the left side. It is subjected to pre-processing, which includes removal of artifacts, noise reduction by applying averaging, median, and low-pass filters, determination of PPX, and obtaining the PP time series. The right picture shows PPG signals with peaks detected and marked. This slide shows a proposed scheme for remote monitoring of cardiac activity. A total of 2 PPG signals and one ECG signals are registered. The created PPG registration device works in the following 2 modes: using a discrete sensor that is external to the device in the form of a clip that is placed on the finger or air lobe. This uses a passing light through the tissues. Reflection of light from human tissues through an integrated sensor built in the device itself. The experimental system employs the ECG development platform for the registration of electrocardiographic signals, which provides high resolution, low noise acquisition of biopotentials. The recorded ECG data are transmitted for the sensor module to a microcontroller unit responsible for initial processing and packaging of the signals. From there, the information is forwarded via gateway device to a computer and cloud platform for advanced analysis, visualization, and secure storage. This modular design ensures flexibility, scalability, and compatibility with IoT-based healthcare infrastructure, enabling both local and remote monitoring of cardiac activity. Special attention was paid to the data security and compliance with GDPR regulations, ensuring privacy, reliability, and trust in the IoT-based system. The simultaneous processing and comparisons of the PPG signals obtained from the different parts of the individual body makes it possible to reduce the artifacts introduced in the PPG signal because of movement of the patient's body. results. This slide shows result from linear methods of analysis. These methods are standardized. Table on the left presents the normal values from the linear statistical parameters according to the accepted HRV standard. Table on the right presents the results from the time domain analysis performed on arrhythmia patient and healthy controls. The majority of parameters were significantly reduced in the arrhythmia group, confirming impaired autonomic regulation. The figure on the left shows a histogram of a healthy individual and an arrhythmia patient. Figure on the right. The histogram of healthy individual has characteristic shape of a normal Gaussian distribution, asymmetric bell shape, and the intervals have central mode of 0.78 seconds. In the patient with arrhythmia, a shift of the histogram to the left asymmetric concentration of the intervals around 4 modes, 0.6 seconds and 0.42 seconds. This slide shows results from the trended fluctuation analysis. The top figure illustrates a scaling exponent alpha 1 and alpha 2 obtained from a cardio recording of a healthy subject. As expected, alpha 1 equals 1.14 for short-term correlations and alpha 2 equals 1.32 for long-term correlations, with alpha 2 greater than alpha 1. This separation between short and long-range scaling behavior reflects the multi-scale regulatory capacity for the healthy cardiovascular system, where rapid fluctuations are superimposed on the persistent long-term structure. The bottom figure shows the DFA parameters for arrhythmia patients. Here, alpha 1 equals 0.94 and alpha 2 equals 0.92, indicating not only reduced absolute values, but also the absence of the typical separation between short and long-term correlations. Conclusion: this study demonstrated the patients with arrhythmia show significantly reduced HRV values, SDNN, RMSSD, PNN50, and altered nonlinear dynamics, including convergence of DFA exponent and higher Hertz values, indicating a loss of physiological complexity. The proposed IoT-based framework integrates wearable ECG, PPG sensors, wireless communications, and secure cloud storage, enabling real-time monitoring and continuous data access outside hospital environments. IoT service reduce the gap between hospital-based diagnostics and home-based care, providing care learning system, adaptive treatment monitoring, and cost-effective long-term supervision. Overall, the integration of advanced HRV analysis with IoT infrastructure offers a scalable, patient-centered, and cost-efficient solution for next generation cardiovascular care. Thanks for your attention.
Okay, thank you. Are there any questions? Okay, let's go on with the next paper. The title of the paper is A Framework for ML-Based Intrusion Detection and Prevention, a Containerized Cloud-Native Approach.
Hello.
Hello, you can share your screen.
Yeah. Send.
So do you have a problem for sharing
Yeah,
screen?
I need to share the right.
Did you click the green
Oh, yeah,
button?
I think that's the right one. Yeah. So I hope you all see that.
Okay, we can see and you can start.
Do you see the first slide?
Yes, you can start.
Okay. So yeah, good morning. My name is Nicholas Найденов, and I'm here to present our framework for machine learning-based intrusion detection and prevention, which focuses on the containerized cloud-native approach. You can see the names of the four authors on the right and their affiliations. This work is a collaboration between Sofia University, Malmö University, and the European Spallation Source. So the move to really hope I'm showing the second slide right now. The move to cloud and microservices has expanded the attack surface, making traditional security insufficient. Machine learning is the logical answer, but it suffers from.
Sorry, the slides doesn't change. Do you change the slides? We only see the first slide, the title of the paper and the authors.
Things are not working.
Okay, now there's no problem. You can go on.
Okay, so the move to cloud and microservices has expanded the attack surface, making traditional security insufficient. Machine learning is the logical answer, but it suffers from a critical practical problem. The train serves queue. We train our models on rich, high fidelity offline data, but in production, we need low latency, real-time decisions, and can't afford to generate those same complex features. This disconnect means models that are highly accurate in the lab often fail in production. I have no idea why this doesn't work properly.
I think you shouldn't make full screen. If you don't make full screen, I think we can see when you change. But now we cannot see.
Okay.
Do not make you can go on like okay.
Okay. So do we have the presentation now? Slide number, the evolving problem.
Okay.
I hope you see the slide, evolving problem. Okay, so moving to the next one, solution and contributions.
But we cannot see now. Maybe you can download to the computer and open as PowerPoint.
Now? What about now?
No, we cannot see.
Interesting. Can we go with somebody else's presentation right now? And I try to fix this in the meantime.
Okay, you can stop screen sharing. We can go on with the other participant. So the title of the next paper is Big Data Analytics-Based Design Strategy Research for Regional Culture Brand Packaging. Our authors here. Okay, the title of the other paper is Effects of Virtual and Mixed Reality Environments on Heart Rate Dynamics During High-Intensity Gaming.
Hello.
Hello, you can share your screen.
Yes. Do you see the presentation?
Yes.
Okay. Hello, my name is Penja Dimitrov Lebamovsky, and I'm from Bulgaria. I work at the Bulgarian Academy of Sciences at the Institute of Robotics. The title of the article is Effects on Virtual and Mixed Reality Environments on Heart Rate Dynamic During High-Intensity Gaming. On this slide you showed the content of the presentation, which include introduction, virtual reality, mixed reality interaction, heart rate variability and virtual reality, mixed reality, methods for games development for virtual reality, methods for heart rate variability analysis, results, discussion and conclusion. In our study, we investigate the impact of virtual reality and mixed reality on the heart rate variability. On one of the main system of the human body is the autonomic nervous system. That system consists from two more systems, parasympathetic nervous system and sympathetic nervous system. When our body is in the relax, we activate the parasympathetic systems, and when our body is on stress, which can be physical or mental, we activate the sympathetic nervous system. In recent years, the virtual reality and mixed reality technologies become one of the fastest growing areas in the modern information system. In compared with the traditional computer, virtual reality and mixed reality environments provide immersion and presence that is different from the traditional computer. On this slide, I showed the two systems, virtual reality and mixed reality. The virtual reality, the helmet that is using in our study is the Photon 3D Pro VR headset. This headset acts as a monitor and does not use additional software or sensors. Interaction is made programming software and keyboard, joystick, controllers and mouse. Virtual reality is the technology for fully immersing the user in the environment. On the other hand, the mixed reality integrates real and virtual elements. The helmet that is using is HoloLens 2 on Microsoft mixed reality. one of the most commonly used biophysiological indicator for assessing the autonomic nervous system is the heart rate variability. As we say, the heart rate variability reflects the function and the time intervals between the successive heartbeats. We activate our parasympathetic system and automatic sympathetic nervous system when our body is in stress and or in relaxation. Very important for developing VR or mixed reality games is the mathematical methods. In this study we use the transform 3D, and because the transform 3D, that is the mathematical and informatical parameters. They can be presented by matrix or quaternions. With help of the transform 3D we can rotation, translate, or scaling object. With the help of these methods, it's possible the user to look around in the virtual environment. That is the pitch, yaw, and throw. That is we can rotate our head on the three axes, X, Y, and Z. Very important sensor that is using for HoloLens 2, that is the eye tracking, the head tracking, voice commands, and etc. and head tracking. In our study we investigate data for experiments, are 22 person. We use linear and non-linear methods to investigate the heart rate variability and virtual or mixed reality. Linear analysis are based on the spectral methods, on the non-linear methods such as Poincaré-Plot, entropy, sample entropy, the trended function analysis, and etc. On this slide I show you the view of the game. On left the game is in virtual reality, on the right in mixed reality. On this slide I show you the result of our study. We compared Relax with virtual reality and Relax with the HoloLens mixed reality, with the help of the linear methods, time domain analysis, frequency domain analysis, and non-linear domains. You can see most of the parameters are significant. As the result of the time domain analysis showed decreasing in some of the parameters, mean error, SDNN, RMSD, and PNN 50%. Effect be more pronounced when using the VR headset compared to the HoloLens. The frequency domain analysis revealed significant difference in the autonomic regulation. The analysis of non-linear parameters provides a deeper insight into the dynamics of the autonomous regulation when using VR, virtual reality, and mixed reality headset. And non-linear entropy indicates when using the VR headset, reflecting reduced complexity and predictability. The presented study demonstrates the use of virtual reality and mixed reality headsets. This headset has different effect on the heart rate variability during extreme gaming. We are using time domain and frequency domain parameter and VR headset Photon 3D Pro and mixed reality headset HoloLens 2. Thank you for your attention. I can show the part of the game. You can see this is the game for virtual reality, and thank you for your attention.
Okay, thank you. Are there any questions? Okay, let's go on with the next paper. By the way, did you solve the problem, Nicholas Naidenov?
Looks like it happens when it's in full screen, yes.
Okay, you can share again. Okay, we can see your screen. Please try to change, and now we can make sure that we can see. Please try to change the pages before starting.
Yeah.
We only see the first page now. Only the first page. Maybe you can change from the bottom left corner. Now the third page. Can you please try changing pages?
Yep,
Now we see only the third page, our solution and contributions.
Yeah, that's right. That's the page.
Okay, please try to go on the other page so we can make sure.
Let's say.
No, it doesn't change. We only
No.
see the third page. When you click, it doesn't change on our site. So I think try downloading it as a PowerPoint file and open it from your computer, not from Canva.
Not on my computer. Do you see the evolving problem? Or?
No, we only see the third page. Now, evolving problem we can see.
Yeah,
and
that's the page I'm on.
Change again. I think we can go on with the other paper and you can again try solving the problem. But again, I suggest you to download it as a PowerPoint file to computer. So the title of the next paper is Automatic Anomaly Detection in Panoramic Dental Radiographs using a YOLO V8-based deep learning method.
Hi everyone.
Hello, you can share your screen.
Yes. Okay. Everyone, and welcome. My name is Tarık Yılmaz, and I am a master student in Electrical Electronic Engineering at Sakarya University of Application Science. Today, I am excited to present your research titled Automatic Anomaly Detection in Panoramic Dental Radiographics using a YOLO version 8-based deep learning method. In this presentation, we aim to demonstrate how we can achieve high effective result in critical fields like dentistry without resorting to the most complex and heavy computational models, or focus in a combined and model lightweight architect YOLO version 8 with intelligence data processing techniques to achieve high performance. Literature on artificial intelligence, as you know, in recent years, artificial intelligence and deep learning methods and significantly contributed to clinical diagnostic and production in dentistry. especially the automatic detection of anomalies, success queries, decay, impact teeth, and precal lesion has become possible, which is critical for clinic workflows. The literature shows that many algorithms, CNN, UNet, and faster RCNN, dental imaging method table. In this table, we see several case studies from the literature and the methods they employed. Researchers from Lee to Byte have used various models, CNN for decay detection, UNet for segmentation, and even older version of yellow version 3 and 4 for object detection. Our work follows this prognosis applied the most current version, yellow version 8, to panoramic radiographies. Okay. Challenge and objectives. The accurate detection of dental anomalies is critical for clinical diagnosis and treatments. Deep learning offers the capability to automatically and quickly solve these challenge detection problems. Our specific objective in this study was deployment YOLO model capable of detecting dental caries, preapical lesion, and impacted teeth within panoramic dental radiographies. To achieve this, we utilize and fully labeled dataset of 1005 X-ray images. This slide state of art in deep learning. Looking again at the state of art, we see different architecture excelling at different tasks. CNN-based methods have shown high accuracy in caries detection. UNet has proven high efficiency for analyzing radiographic data, particularly segmentation. RCNN variants have succeeded in location. The YOLO series, however, has proven its advantages in speed and accuracy for dental application. From version 3 to version 5. Research gap and our contribution. So with all this exciting research, what is the gap that we are feeling? We observed that most studies tend to focus on limited datasets or detection of only a single type of anomaly. This is where our contribution comes in. Instead of moving towards overly complex and computationally heavy models, we choose the lightweight and efficient YOLO version 8 architecture. We then tested this model in a multi-class detection setup and performed a detailed class-based performance evaluation. Most importantly, we the model's performance not through architecturally complexity, but by analyzing the impact of effective data augmentation technology. Our goal is to prove that a simpler, faster model can be highly reliable when supported by my smart data strategy. Methodology overview. Our methodology is straightforward and consists of 5 steps. Data collection. we get her the Dentex dataset with 1005 full labeled panoramic X-ray images. Forward conversation, we transformed the annotation from COCO to YOLO format. Data augmentation, this is a case step. We applied it bricks, contrast, blur, and spatial transformation. Model training, we trained the latest model YOLO versions 8 Nano using 70% training, 5% validation, 25% test split. Performance evaluation, finally we evaluated the model using started metrics like precision recall, mean AP at 0.5 and mean AP at 0.5 to 0.95. Dataset compensation, the Dentex dataset we use it contains for anomaly classes, but in suffers from a significant class imbalance. As you can see, preapical lesion is far less common the deep caries and impacted. This imbalance makes it difficult for models to learn the classes. This is where data augmentation becomes essential. We increased our training set of 705 images by approximately sixfold to 2,844 images. This was the most important step we took to improve the model's generalization and ensure to identify these underrepresented anomalies. Data augmentation techniques, as anyone who works with medical images know, deep learning model required a large number of samples to generalize effectively. However, dental X-ray datasets are often limited. Data augmentation artificially this limited data. YOLO architect advances in it achieves a height general COCO dataset and incredible processing speed of 150 FPS. We use it the light test version, YOLO version 8 Nano, training for 100 epochs with a batch size of 4. Also, hardware and NVIDIA RTX 3050 Ti. Performance result, and here are our results. You can see the class specific performance for our augmented model. Our model's overall precision is 56.3%, and this overall recall is 55.8%. Experiment result, caries impacted that and lesion are successfully with confidence score ranking from 0.40 to 0.80. This is visual proof of the model practical performance and clinic viability. Comparative performance analysis. This table is the most important summary of our core idea. Here we compare our model much more complex and large model from Harmanji et al. Study success rating on it, faster RCNN, and even the transform-based models. Our models with its 52.5%, 50 and 33.4% is highly comparative with the cross from models. For example, 52.8 or 5-star CNN 54.3. It means that with a simpler architecture but a smarter data strategy, you can complete heat to heat with complex. This is enormous potential for developing practical fast system. What have we achieved? We deployment a clinical variable systems that can detect multiple anomaly types with high confidence using yellow version 6 nano and augmentation. We demonstrate that this simpler architect can achieve competitive performance compared to complex model. This opens to for faster, more efficiency, automated diagnostic systems. Thank you for your time.
Okay, thank you. Are there any questions? Okay, let's go with the next paper. I think we completed all of the presentations. Only one. Did you solve the problem, Nicholas Naidenov?
Hello, good morning, sir. I have a question.
Sorry, yes, please.
Yes, I am among the person that is going to make a presentation in your group, but tomorrow.
Okay, you can present tomorrow.
No, no, I have some things and traveling that I will make tomorrow. I don't know if there is a space after this one. If there is a space, you help me to make my presentation today. Is it possible that one?
What is your station number and paper ID?
Paper ID is 342. And yes, session 10.2.
10.2,
Yes.
3, 4.
Yes,
2, okay.
interpretable
Okay,
machine learning and deep learning model.
Interpretable machine learning and deep learning models.
Yes, sir. Yes, I review paper.
3, 4. Okay, after this one.
Yes, sir. Okay, thank you.
Okay, so Nicholas Naidenov started screen sharing.
Let me check if you see
We see your screen.
entire screen or
we only see the title page, first page.
okay, second page.
Now it changed the evolving problem.
Yeah, okay. So I think I went through this problem and I think it's working now. So it was about the train search skew where we train our models on rich offline data, but in production we need low latency. And there's a problem with working with complex features. So our paper addresses this challenge with a modular dual workflow, our solution. Hopefully that's what you see. Cloud native intrusion detection and prevention system. It has two main contributions. First, we provide a complete orchestration blueprint for deploying the system as a containerized microservice-based cluster designed for platforms like Kubernetes. The second, we propose a minimal overhead online workflow that involves not involves but solves the train search queue. It uses extended Berkeley packet filter, eBPF, high-performance probes in the kernel, and a real-time agent that replicates the full rich feature vector on the fly. This way, we bridge the gap from an academic model to a practical, resilient, and maintainable cloud security service. However, we are not starting from scratch. We saw a distinct gap in the related work. While prior research has containerized tools like Snort, they often rely on simpler management, like Docker Compose, which lacks true orchestration capabilities, like automated scaling and resilience that Kubernetes provides. Our work directly builds upon a validated two-stage machine learning framework from our foundational thesis. The architecture of this framework is presented on the left side of the slide. I hope to see a picture there. This original framework was highly effective, but it was an offline-only proof of concept. Our paper provides the architecture to operationalize this model in a live real-time environment. So the central architectural idea is a dual workflow design that decouples real-time operations from offline analytics. This is critical because it allows each workflow to be independently optimized. So workflow 1, the real-time component, is engineered for speed. It needs minimal overhead. In contrast, workflow 2, the offline component, is engineered for depth. Do you hear me, see me? Just want to make sure. Yeah, okay. This is where we do the heavy analytics in the workflow tool, forensics, and model retraining. Yep. So drilling into workflow 1, our real-time pipeline, there are 3 key steps. First, data probing. For a production system, we recommend custom lightweight eBPF programs because they run in the kernel. They have lowest possible resource footprint. Second, real-time feature engineering. A user space agent ingests a raw event stream from those eBPF probes. It maintains an in-memory state of active flows, that's communication flows, and calculates the full statistical feature vector on the fly. It's replicating the exact format of the training data. And third, online inference. This fully formed feature vector is fed to a high-speed containerized machine learning model for an immediate decision. This process should solve the transfer skew. Now let's look at workflow 2, our offline backbone. For this task, we recommend KubeShark. Its strength is deep packet inspection, plus its ability to automatically enrich all data with deep Kubernetes contexts. So we don't just see stuff like IP addresses and ports, we see which port, which service, which namespace the traffic belongs to, and this rich packet capture corpus is then processed with high-fidelity feature extractor, like the CIC flow meter, which we used in the thesis, to build our training dataset. This is where we train our most powerful models, and the feedback loop then periodically pushes these new smarter models to update both workflows. A key feature of the framework is its modularity. The two-stage design allows us to swap algorithms based on specific needs. For stage 1, the anomaly detection, we analyze the trade-off between autoencoder with its strong generalization in diverse environments, and isolation forest for a significantly faster inference. For stage 2, detailed attack classification, we use HTBoost. It was selected for its consistently superior accuracy in fine-grained multi-class classification, allowing it to precisely identify what kind of attack we are seeing. I didn't include results here because this is not the main point. The point is that this microservice-based design maps directly to cloud-native deployment. We've provided a concrete blueprint for Kubernetes. eVPF probes are deployed as daemon set, which ensures they run on every single node. The machine learning services are scalable Kubernetes deployments. This cloud-native approach unlocks critical operational advantages like scalability for any traffic load, high availability. A failed container can be restarted automatically, zero downtime updates. We can use standard rolling updates in Kubernetes to push new models from the feedback loop without even taking the security service offline, so it updates on the go. This also enables actionable response. The system can automatically generate Kubernetes network policy to isolated threats. So to conclude, the paper presented a modular dual workflow architecture for an ML-based IDPS. We successfully upgraded a previously validated offline ML prototype into a fully operational cloud-native system. A critical contribution is solving the train-serve skill problem by using eVPF and a real-time agent to replicate feature-rich vectors. Finally, we provided a concrete blueprint to orchestrate this entire system as a scalable, resilient, and maintainable container cluster using Kubernetes. For future work, we will focus on expanding this foundation. First, empirical performance benchmarking. Second, automated MLOps implementation, and then enhanced response mechanisms to move from detection to active prevention, such as post-spot isolation and others. So I conclude with some contact information for me and the other authors. Thank you for your time. Sorry for the delay, technical problems, and I'm here for questions.
Okay, thank you for your presentation. Are there any questions? Okay, thank you. So, 342, you can present.
Okay, sir. Thank you. Let me see my screen. Sir, can you see my screen?
Not yet. It's loading.
Okay.
Yes, now we can see.
Okay. So is it changing?
Yeah, yes, you can
Okay.
go on.
Okay, thank you very much. Good morning, sir. My name is Ismail Abubakar Boboy. I'm from Electrical and Electronics Engineering Department near East University, Nicosia, Northern Cyprus. I want to make a presentation on the topic interpretable machine learning and deep learning models. Sir, I don't know. Can you hear me?
Yeah, yes, we can hear you.
Okay, thank you. Making a presentation on the title Interpretable Machine Learning and Deep Learning Models for Prediction of Chemical Oxygen Demand and Biological Oxygen Demand in Industrial Wastewater Treatment Plan for Better Operational Performance and Cost Effectiveness, a review paper. First of all, we will talk about the background. Number one, wastewater treatment plant is a facility designed to receive waste from domestic, industrial, and commercial sources, and to treat it, manage it before it's released back to the sources, that is water, or before you reuse it. A wastewater treatment plant is characterized by three components: biological process, chemical process, and physical process. Effect of raw sewage on aquatic and public. Number one, among the effects that is affecting that the wastewater treatment plant have the water degradation. That is when pollutant is increased, it will decrease the quality of the water. Number two, habitat destruction. It will destruct the habitat of the animal by by harming the aquatic life, and it will affect the human, that is public, by direct accumulation, that is by consuming and it will spread the waterborne diseases such as malaria, typhoid, hepatitis, and cholera. Then among the effect, it will contaminate the ground source water, and then it will raise the food security concern. The importance of COD and BOD in design, operation, and monitoring of the wastewater treatment plant. Number one is an organic indicator. It's an organic indicator because COD, that is chemical oxygen demand, is the amount of oxygen, total amount of oxygen required to oxidize both biodegradable and non-biodegradable substances. While BOD, that is biological oxygen demand, is the amount of oxygen required for a microorganism to break down the organic matter in a specific period of time, usually 5 days. Among the importance of COD and BOD, then the monitoring of the treatment efficiency. The value of the estimated value of COD and BOD, the difference between the values before and after treatment, it will indicate the effectiveness of the treatment. And then the estimated value of COD and BOD will help in determining which type of the treatment plant and what the capacity it can take. Then it will help in compliance with the regulatory, with the environmental regulation. That is, the regulatory body set the amount of COD and BOD in the treated wastewater that is allowed to discharge in the environment. Then it is indicator, the indicator of treatment health process. That is the high number of COD and BOD in a treated wastewater. It's indicating the failure of the treatment process. Then the access to the organic lot, it will quantify the amount of the organic matter that entering into the wastewater treatment plant. So wastewater treatment control, the attention of researchers over the years has been drawn to the wastewater treatment taxes. So numerous method has been developed by the researchers over the years. Such methods are activated sludge, membrane bioreactors, chemical coagulation, sequential batch reaction, UV light disinfection, ozone gas, and much more. So, and just to mention the few. All the mentioned methods, they are characterized by resource intensive. They consume a lot of energy. They can waste a lot of chemicals. They are characterized by labor, waste of time, and error subjected to human error. So these characteristics call for the intervention of artificial intelligence into the system. So the objective of this review is to analyze the development of interpretable machine learning and deep learning model in wastewater treatment plant. Number two, to highlight the benefit, limitation, and future direction. Number three, to propose an integratable framework for improved accuracy and transparency. Number one, the overview of the machine learning models and deep learning model in for COD and BOD prediction. Machine learning and deep learning model, they are essential for wastewater treatment plant efficiency. In order to, since that we listed those methods, they are resource intensive, they are subjected to error and other problems. So machine learning and deep learning model are essential for the treatment efficiency. So number one, traditional, among the method, another method is the traditional wet chemicals method. This method, it is very slow and it's costly. That is the problem with the method. But machine learning models can capture nonlinear relationship in a wastewater data. So machine learning as a subfield of, and as a subset of artificial intelligence, it has the ability of learning from the data without the explicit guides or without the human intervention. It can learn from the data and make the prediction based on the data that is provided. Number two, the study examined the traditional, these studies examine the traditional, advanced, and hybrid models for wastewater treatment plant. For wastewater, for COD and BOD treatment plant. Number one, the traditional machine learning models such as linear regression. The literature review shows that the linear regression is a simple and interpretable. It's a simple to understand. The interpretability can be met easily, but it has a poor performance in nonlinear data. such as nonlinear data, such as wastewater treatment plant data. Decision tree is another machine learning algorithm, which is easy to understand, but is subjected to overfit. It can overfit easily. While random forest is the third machine learning models, which has a little or no overfitting because of the structure of the random forest. It can handle high dimensional data, but the interpretability here is very difficult. It's less predictable. While advanced machine learning models such as gradient boosting, for example, including XGBoost, light GBD, GBM, and cat boots, they have a highly accuracy. They can scale. They have the scalability, but the computational expensive. It is very expensive to implement it. While deep learning, such as artificial neural network, convolution neural network, and recurrent neural network, it has the ability of capturing capturing the complex temporal and spatial pattern, but it requires the large data. They are calling the deep learning model as a data hungry. It cannot perform in a very small data set, so it needs a very large data in order to give you the accurate. And it lacks interpretability. And interpreting machine learning is a very difficult. While hybrid model, the hybrid is a combination of deep learning and machine learning model for improved accuracy and interpretability, though it's a computational expensive. Hybrid is the process of combining the features and the advantages of machine learning model with the features and advantages of a deep learning model in order to lump them together, to merge them, and in order to enhance the accuracy and interpretability. So model comparison, the literature review, model comparison based on accuracy, robustness, and scalability. The literature review shows that the advanced machine learning models such as XGBoost outperform the traditional ones in accuracy, such as it has low root mean square and mean absolute error square, very low, and the high coefficient of determinant, that is R square. Is enable number two is enable the models like gradient boosting and random forest handling noising capability, high dimensional data well. Then the deep learning model, scalable, effectiveness, but require high data tuning. So interpretability in machine learning. Machine learning models predict COD and BOD effectively, but it's considered as a black box. That is, there is no interpretability, no transparency. So interpretability is crucial. It is required for the trust, compliance, and decision making. For the compliance for the management of wastewater treatment plants is required because it is the one that will reveal the factors that influencing the model performance. So explainability enhance model transparency in wastewater treatment management. So explainable techniques such as they are, just to mention, we have sharp, lime, and others. The case studies here, the sharp in random forest is based on the review, it showed that it identified the temperature, flow rate, dosage as COD drivers. Then when lime in deep learning models explain the BOD variation into oxygen and organic matter. So the research gap, it's been discovered from the literature, there is no integrated framework that combine interpretability and transparency. Number two, there is a limited studies that is addressing both COD and BOD simultaneously. Then number three, there is a lack real-world validation and cost effectiveness in the studies that is concerning the wastewater treatment plant. Then there is an absent standard mathematical framework. Then there is a few study that is linking the model performance to the cost effectively, to the cost effectiveness. That is what is discovered from the literature review. So the future direction, this review is recommending for an integratable machine learning and deep learning model to integrate them together to make a hybrid based on the statistical model, to develop a visualization tool for transparency, for decision support, then to implement the real-time COD and BOD prediction system, then to design scalable cost effectiveness architecture to enable cross-domain, then to focus on sustainability-oriented models. So the conclusion, deep learning and machine learning transform wastewater treatment through accuracy and efficiency. Interpretable machine remain challenge for adoption because lack of the transparency. So in combining the sharp and lime with hybrid models promote transparency. So outcome, sustainability and efficient wastewater system. Thank you for listening.
Okay, thank you. Are there any questions? Okay, we have completed all of the presentations. Dear participants, on behalf of organizing committee, I would like to thank you for your scientific contribution to the Congress, and we hope to meet you in next Congresses as well. Now I am ending the session. Thank you.
Thank you, sir. Bye-bye.